Okay, hi everyone. Thanks for joining today. So today it's my pleasure to welcome Iddo, who's starting as an associate professor in computer science at Boston University. I think currently he's an adjunct professor at Columbia, and previously he was a lecturer at MIT in Eek's department. He's researching on machine learning, AI, and computer vision, and has over 70 publications in the area and over 5,000 citations, and has won multiple competitions in computer vision, as well as multiple best paper awards in machine learning. And today he's going to be telling us about some of his work on learning to learn courses. So thanks so much for joining us today. And yeah, whenever you're ready.
Okay, so thanks so much for the invitation, Armando, and the introduction, Osbert. And today I'm going to talk about learning to learn courses, which is joint work with over 30 people in the past 2 years, a team of students, researchers, colleagues, faculty from MIT, Cornell, Columbia, Harvard, and other universities. This work has led to half a dozen publications, and today I'm going to talk about 3 of them, which are the latest ones. And so I'm going to talk about a neural network solving, explaining, and generating university math problems by program synthesis and few-shot learning at human level, a data set and benchmark for automatically answering and generating machine learning final exams, and the data set for learning university STEM courses at scale. So about 6 months ago, or a year, there was a misconception that neural networks could not do math. On a standard benchmark that's called a math benchmark, the accuracy was between 5 and 8%, published in a journal saying that this benchmark was a really hard problem. And we moved that needle to 81% automatic accuracy in November, December of 21. And we extended that benchmark to undergrad math, from high school math to undergrad math courses, specifically the math courses at MIT. And so this result from 8% to 81% is what I'm going to talk about today, and how we accomplished that, and I guess why is this happening and how this is happening. So specifically, a result of over 80% accuracy on math courses and questions from math courses, problem sets, quizzes, and exams owes its success to program synthesis and few-shot learning, and program synthesis specifically using large pre-trained language models that are fine-tuned on code, namely OpenAI codecs and the like, and few-shot learning based on examples, question-answer pairs examples that are given to these fine-tuned models. So before we begin, I'd like to show examples of simple questions. Here are simple questions from various math courses at MIT, from single variable calculus and multivariable calculus, differential equations, intro to probability and statistics, linear algebra, math for CS, and another course from Columbia, and the math benchmark. And you can see the input questions here are quite simple, and the output could be numeric, equations, graphs, images, or symbolic. So we started this work 2 years ago, and we started tackling these questions by tackling a single course. It was MIT's Machine Learning 6036 course, and problems from the P-sets that are given out regularly every week in this course. And we started by using transformers pre-trained on text and graph neural networks to solve that specific course. However, we quickly realized that our approach, which was augmenting data and generating thousands of examples for each question, was overfitting on that specific course. And while it was doing really well, it didn't scale up to any other course. So the performance was better than the average MIT student that did 93 in the same semester, And here's a breakdown by topic. But still, this was completely failing on any other course. If you took this model and tried it on linear algebra, it would get 0. The gist of this approach that we did 2 years ago was turning the questions into expression trees and looking at this computation graph of expression trees and getting the solution. But this limitation that it didn't scale to other courses and that it overfit the specific course was a real limitation, which we overcame using program synthesis and few-shot learning, which is what I'm going to talk about today. So essentially, we had the realization around September, October of 21, that rather than representing the text of the questions and the numbers and the entities of the question in text, there is a vast amount of data of programs and text out there of decades of programming that can be used. And our insight was to turn the questions into programming tasks. So what happened is we tried this on a linear algebra course, and we took Gilbert Strang's textbook, and we took questions from his textbook and turned these questions into program synthesis tasks. Instead of solving the question, write a program that would solve the question. And all of a sudden, the needle moved from 8% to around 60, 70% without doing anything more than just write a program for that question. And that was, said, well, okay, we went to Strang the same week, and he said, well, you know what? Why don't you take a look at the big courses, the big math courses at MIT? Take a look at calculus, differential equations, and probability, and try those. And we went and tried those. And 2 days later, we came back to Strang and said, look, we're demonstrating now live, and we have about 70% accuracy on these courses as well. And that was fine, but a lot of that 70% accuracy involved formulating the questions in a way that we can turn them into programs, and we wanted this to be fully automated. So our initial approach was to turn questions into program synthesis tasks. We used OpenAI Codex, though today there are a dozen language models that do program synthesis. Codex was pre-trained on text and fine-tuned on code. It generated the code for solving the question. We executed the programs in Python. The result were answers. They could be numeric, texts, or plots. We could prompt the model, not only give it zero-shot learning, but prompt it by examples to improve the accuracy. And verify, perhaps importantly, verify that it's not overfitting by trying this on other courses, namely a Columbia course that was curated and never published online, like the MIT OpenCourseWare courses that are available online. And then we scaled this up quite quickly to multiple courses. So our base approach was program synthesis. We took a question, we turned it into a programming task. Then we added few-shot learning on top of this to improve accuracy and make this automatic. We automatically generated the program, executed the program, and then once we had the program and evaluated the answers, we said, well, why not also explain the code of the program automatically, because this model was trained both on text and code. Then given the code, you can use it to also generate the text explaining the solution. And finally, we said, well, okay, now that we have this system and it works on half a dozen math courses at MIT, why don't we just use it to generate more questions for a course that we're running? And that's what we did. We automatically generated new questions that were indistinguishable from the human written questions by the students themselves. So I'll start from the initial insight and then build this up by steps and explain all the the processes and scientific discoveries along the way. So our initial eureka moment was take a question like finding the distance between points and turn it into a program synthesis task, write a program. This is oversimplistic, but models, language models like GPT-3 don't know what the magnitude of a vector is, a specific vector. They know the concept of the magnitude, but they didn't know math. Then we took this to more elaborate questions like computing the reduced row echelon form of a matrix and said, write a program to compute this reduced row echelon form. And the program is a bit more elaborate. And then we can use the program to compute the reduced row echelon form of a matrix. And finally, running the program results in the answer. And so we looked at these courses, the 5 big math courses at MIT, and took the problem sets from each of the courses and used program synthesis with few-shot learning and explaining the solutions and passed all the questions through this automatic pipeline. Now, sometimes it was the case that we just took the question and added write a program. Sometimes we needed to say write a program using SymPy, which is a symbolic math library. And sometimes we added few-shot learning, which is question code examples that are similar, but are different than the new question to prompt the model to do even better. And this was fully automatic, only with 3 types of write a program using SymPy or using simulations, which I'll describe. That's all that was required without any other change to the original program. And so we generated over 500 examples pretty quickly. And then we stumbled upon probability and statistics courses. Initially, the approach of write a program using SymPy to solve a probability question did not work. But then we considered that probability questions have a lot to do with not only program synthesis, but probabilistic program synthesis, which merges the fields of probability and program synthesis. So what we did is added write a program using simulations, essentially changed the question into a programming synthesis task, where the task generated a program that asked to simulate, to actually draw and do some Monte Carlo or other simulation, and running that simulation resulted in the numerical answer, and we reached over 90% in the probability courses. And that's the addition that actually helped us solve the probability and statistics courses. And so looking at automatic accuracy, which is what was interesting on the mathematics courses, we saw that GPT-3, which was only pre-trained on text, did about 10 to 20%. And using program synthesis, improved this to 70%, to 80%. And using few-shot learning, increased from 80% to 90%. We will never claim 100% because you can always come up with harder questions. But you see the ingredients here. The main ingredients are program synthesis, which turns the question into a structured representation, brings in 3 decades of programs and packages and libraries. And then on top of that, few-shot learning, another 10%. And all this from previous state of the art, which was between 5 and 8% before this work. Okay. Here is how the data set looks like. Here's an example of 25 questions from 1805. You see the name of the course, the topic, the problem, the input, the program. It's just the first line of the program code, the explanation, and the questions that were solved by zero-shot, few-shot learning versus the GPT-3 responses, and the nearest questions for each question, which are the nearest questions based on an embedding.
Sorry, one quick clarification. So this is vanilla codex. It's not fine-tuned or anything. It's just the...
Right. It's vanilla codex with few-shot learning. And I'll explain what that means.
Okay.
So few-shot learning means that we take codecs, but we embed all the questions. And then we compute pairwise similarity between the embeddings. Okay? And then for questions that cannot be zero-shot, we rank the other questions that were zero-shot by similarity to their embeddings, and then use that ranking to select the question code example for few-shot, namely to add that to the prompt. Okay? So essentially, instead of just prompting it with the write a program using SymPy or using simulation, we give it the examples that will help it do that efficiently. So let's start with the basic differentiation. GPT-3 on the left, as expected, doesn't do math. It doesn't know the magnitude of a vector. It can explain what the concept of the magnitude is, but could not compute the magnitude of the vector 1, 2, 1. Whereas using codecs or another program synthesis model allows to write a program that computes this magnitude. So why is this happening? Why does program synthesis solve this or move this from 8% to 80% of few-shot learning? Well, the reason is that programs can always be represented as trees. Whether it's an abstract syntax tree, they're structured. Programs bring in a wealth of 3 decades of programming libraries that can be used. If the questions are in astrophysics, you can use AstroPy. If they're in math and linear algebra or symbolic computing, you can use SymPy, etc. These are 2 main reasons. So we looked at this and said, well, we're doing few-shot learning, we're using codecs. Can we use this to generate new questions that we can actually give in courses? And will these be good questions for students? So we did a survey, IRB approved, with the students, and the students could not distinguish between the new generated questions or human questions. They knew that human written questions were better, were more likely to be human, but from the generated questions, this is like the confusion matrix shown here in this plot, were equally likely to be human or machine generated. And generating new questions is as simple as putting the 31st questions and asking for the 31st one and completing that. We also generated explanations. So given the code, this is just a toy example, but we have this for problem sets, ask the model to generate an explanation, whether it's line by line or, in this example, generate the explanations. Here is the survey that was given to the students. They were given 60 such example questions. They weren't asked to solve the questions, but just to rate the appropriate of the question for the course, difficulty level, and whether they think it's human or machine generated. And as you can see on the right, the machine generated questions seemed equally likely to be human or machine generated, and the level of difficulty was quite similar. What's interesting is if we take the questions in the math courses and embed them first to 2048 dimensional space, and then, for example, to a 2D space where we can visualize things, we see the questions being clustered based on the courses. So you can see the linear algebra courses there on the top right. You can see the calculus courses, differential equations on the left. And you can see the probability courses in math or computer science, which is also heavy in probability and statistics, on the bottom right. Here's a breakdown of the packages that were used. We automatically only said using SymPy, and that prompt produced other imports automatically. You can see the breakdown by courses. And then we said, let's scale this up to dozens of courses. Can this now work not only for the math courses? And so we scaled this to multiple STEM courses. By the way, the data, models, and code are released. So under MathQ, it's available. Everything we just described, I just described, is available online. And we released a data set a few months ago called STEMQ, which had 27 courses across a dozen departments and 7 universities that were curated, solving and explaining and generating new questions for each of these courses across different disciplines. And so when we look at the embeddings and visualization of courses, rather than just in math, but across disciplines, you start seeing interesting things about the data of courses and the disciplines and the curriculum and the prerequisites between courses and the relationships and the usefulness of topics you learn in one course to another. And so you see here on the top right, a cluster of questions from probability and statistics courses from MIT and Harvard. You see on the left side a cluster of questions from MECI courses, and then from chemistry and material science and engineering. Then you see Euroastro. Below you see microbiology and geobiology. And on the center you see physics and quantum physics. And then intro to astronomy related to physics. And on the right, you see a cluster of ECS and Cs and math courses in between and physics courses. So this gives us a sense of which topics and which courses are being used for other courses. And we can build a graph of courses and a graph of questions and see which courses are required for few-shotting, which other courses. For these STEM courses, here are examples of pipelines from different courses, such as signal processing and intro to ML. And so you see whether we take the question as is, or say write a program using SymPy. Here are questions from intro to astronomy. In intro to astronomy, something that helps is adding constants. So some constants that are specific to the field. And here's a question from number theory. And so this first follow-up was all about scale. Can we extend this to a large number of courses, around 27 courses at first? The next step, after we scaled and saw that we're not overfitting, the next question was, well, this is all nice, but you're doing quizzes and problem sets. What about the midterms and finals? It was thought that the midterms and finals only humans can write and answer, and probably those were difficult for these approaches. And so our next challenge was tackling final exams, and we chose machine learning since I was teaching machine learning for 2 years every semester. And 6036 was a huge course of undergrads at MIT. So here is the final exam of MIT 6036. It's 500 students taking the exam in indoor track and field. And the question was, can we have the machine do this exam in a few minutes for all the semesters? And the results were quite surprising. They were on par with the human performance, but there was a huge limitation that we couldn't handle questions that relied on images. So here are the approaches. You can see zero-shot GPT, 3 few-shot with GPT-3, GPT-3 with zero-shot learning, and chain of thought. Chain of thought is just saying, let's think step by step in the question. And codex with zero-shot, codex with few-shot. And we compared these results. And these results were broken down by semester, by each of the finals, and by topic, and we're reaching human level. Except that these ML finals, and the data set is also available, did not include questions that relied on images. Okay? And the way these were evaluated, we took the same TAs that graded with me the class during the end of the semester, and they graded one more student, namely a machine student. Instead of a human, instead of grading 500 students on Gradescope, they graded one more. And the results were at human level, but not the image questions. So the image questions were taken out, and at the time we couldn't do images. You can think about all the questions and various topics that you can draw on the board, or you can draw using any package you'd like. And those are kind of difficult when they contain information about the question. You could draw a neural network, for example, and that neural network will contain some weights or some values, and you need to pick that up. And there are so many ways you can present visual information. And finals and midterms have that visual information. Okay. And so what we're doing now, and that's one limitation. The second limitation was at the time we didn't handle proofs. So if you'd asked a linear algebra question, given two matrices S and T, they are positive semi-definite. Is there sum or product? Is that positive semi-definite or not? And if so, prove. Okay, so these were our two main limitations. And we're now lifting these limitations. Our first limitation, questions that rely on images. We're now working on synthesized captions that contain the information required for solving these questions. Fortunately, Archive contains all the tech and the images and PDFs. And again, a program representation is to the rescue here. We've been synthesizing LaTeX code using drawing packages like TXZ for generating images with initial success. And for proofs, again, few-shot learning, converting questions into a presentation, synthesizing code for proving, and then turning these proofs in code into proofs in text. And finally, we're also working on generating the graphs of questions and of courses to design curriculum. The remaining limitation is questions that are NP hard and theoretical complexity. We don't expect, of course, this to factor primes or answer any of those questions or do research questions, and those remain limitations. We've already released all our data and code for the math, STEM, and machine learning finals. So you're welcome to look up on GitHub MathQ, STEMQ, ML finals queue and download the data and code and try it out for yourself. We're planning to release a data set for doing the entire MIT and Harvard undergrad CS and Cs curriculum. Since we're doing over 27 courses right now, we said we might as well just do the 30, 40 courses that it takes for a student to graduate with an undergraduate ECS or Cs from MIT or Harvard. And we're going to release that data set upon publication. We've already curated that data set as well. In conclusion, this shows that we can automatically solve, explain, and generate university level course questions. The key is program synthesis and few-shot learning. Students rated these machine-generated questions that we use this system to generate more questions using machine as equally likely to be human written. We're scaling this up now to hundreds of courses. Reproducibility is 100%. Data models and code are available online. We don't claim 100% automation since someone will always come up with a harder question. So right now we're a bit above 80. And I think that this will have an impact on higher education. It will also advance the residential learning, enable self-paced learning because you can prompt additional data that is tailored to specific students and their backgrounds. You can explain points of confusion and use this as a tool for designing a curriculum rather than by the history or specific people in charge of designing the curriculum based on the data itself and what the data tells us about which courses are required for other courses and the relationships among them. And we're using this in the fall for automatic content generation, machine learning course as well. So with that, I'd like to thank all the 30 plus collaborators in the past 2 years on this. That led to a half dozen publications, and I'll take questions in the remaining 10 minutes.
Okay, thank you so much for the great talk. Yeah, I guess if people have questions, they can just unmute themselves and ask.
Look at the chat.
Yeah, Albert, what's the setup for, so presumably this data set doesn't exist in the nice form that you have curated in, right? Like there's some amount of like transcription and formatting it into a GPT-3 like or Codex consumable form. Like what does that interface, like what does the labeling interface look like? Or if you could show that, that'd be.
Let me share screen and show this.
Yeah.
So here is our data set. You can go into a course and then you have a JSON file. We curated this from PDFs. So this was a mix of automatic tools for extracting text from PDF and students that curated these questions.
Right. I guess what would so if I'm a student, let's pretend, right? Like, let's say I'm a student and I want to contribute to this data set. Like, what is my workflow? Like, I have a piece of paper in front of me, presumably my midterm from, let's say, 3 years ago.
So here's an example. Here's our STEMQ data set. Okay. Say you're a student at Harvard and you have a problem set that you would like to contribute. First, make sure that you have permission and that you own that data set, right? And it's yours and you can actually contribute it. But essentially preparing that is quite easy. You would just take the original question. There are tools out there that turn PDF into text. You would use those automatic tools. Then you would afterwards see and edit if things came out wrong, and edit the original question and do the same for the solution. That's it. I
see. So I would have to type the question kind of as is and then have a solution.
You'd give a PDF to an automatic tool, but afterwards you would verify yourself that this was done correctly. Some quality assurance that there weren't any special characters or other things in the original question, like units and some special symbols, etc.
I see. And these are, I see, only for text ones. And then there's no, and the kind of the chain of thought prompting is not in this interface, right?
Prompting is in the code. It's super simple. I can go there and show this. It's maybe it's kind of overrated. It's all it is. I can walk you through this. All it is just saying, adding to the prompt. Let's think step by step. So I can show this thing here. Essentially, chain of thought amounts to this string that you add.
I see.
Okay.
I see.
And there are different, there are about 7-8 different strings that people have tried for chain of thought prompting and did various benchmarks. But it's not more than that. And chain of thought is very easy to incorporate in any usage of any language model.
I see. And then you are not, essentially by adding that step-by-step string, and then that's a completed prompt, and then there's no more interaction between
right. So we have the question, we turn it into write a program using SymPy or using simulation. We compute the embeddings, we add the few-shot learning, the examples before. So we have the examples, the few-shot examples before, the write a program using SymPy after. Let's think step by step afterwards. And then you can do the full comparison. And the code toggles these options on and off, and you can run experiments with few shot, 0 shot, with chain of thought, without, with SymPy, without, with simulation, without, etc. Okay.
I see.
In hindsight, it's easy because in hindsight, you see the solution already. But getting there was the hard part. Getting to the moment that we realized that program synthesis was the key, was one of the keys, and that few-shot learning was one of the keys. In November, that was, all of a sudden, it's kind of surprising that within a week you move from 8% to 60 or 70%. Usually the improvements are kind of incremental. You don't get an order of magnitude that quickly. And so this is why this was one of our strongest results of the year. Chain of thought increases a few percentage points as well. we didn't introduce that. That was introduced by others. We use that for comparison so that we can show ablation studies and provide those ablation studies for completeness.
Mm-hmm. Yeah, no, this is good. And you're not intervening at any of the intermediate stuff, right? Like you just generated. Let's say hypothetically you were to put this on the internet as a study guide or study aid or something. The student just need to kind of type the questions and then that's right, and then the answer should come out, and then they can submit it onto whatever that god awful physics crap is.
It is available right now, and students can do it right now. So when I'm teaching, I recommend that they use the tools, but before they do that, they solve the questions themselves. Right? But I guess that knowing how to, my take on this is the following: these tools can do their programming exercises and their problem sets, but with a programming exercise that typically would take them 10 hours, they can do this in 10 minutes, probably. And we've tried this in class with 100 students and did 4 programming exercises in this series of 10 minutes after 10 minutes each. But I think the important skill set for the students is learning how to use these tools, right? Think of it as the following. This is informal, but before autonomous cars, you needed to know how to drive. Now you have autonomous cars, you need to do something else. Before this, right, you would solve the problem set, you'd solve the coding exercise. Now you could do this in a few minutes using this and write a program to implement SGD or implement a neural network in PyTorch or CNN in PyTorch, etc. But using these tools correctly is a skill set by itself. So how do you use this automatic tool is the new skill set that they are now learning in class. So essentially, as part of the curriculum, what we're teaching the students is we have a class where we teach them, they all come in with these tools installed. And we had 100 students come in with these tools installed on their laptops and simultaneously had 4 rounds. The first round, 30 of them were able to solve the questions, then 70, etc. So they're learning how to use the automatic tools, which also requires some training, essentially. Their skill sets are now complemented. They're understanding what program synthesis is, what few-shot learning is, what chain of thought is, etc. But we do tell them that they need to do their homeworks themselves beforehand, and then we give them a lecture with the tool and say, oh, the homeworks you did throughout the semester, here's how you can do this later on. Here's how you can prepare for interviews or for your jobs in the future. And this is the next evolution of something that you use in your training, not only
is
the
this
materials.
tool like online? Can you drop like a URL? I want to use it.
Yeah, it's a MathQ. If you Google GitHub MathQ, and you can go there, check out 3 different GitHub repositories.
Oh, I need to actually like figure out how to compile it, I guess, presumably.
You just need to download and install Python.
I see. Okay, cool. This is good. Thanks.
Everything is public.
Yeah.
So I had a question. So you mentioned that you're working on proofs, and I guess I was really curious about that because that's, there's not a bunch of code, presumably, that Codex was trained on that's doing theorem proving. So I'm wondering how successful that's been and how you dealt with the fact that there's not all this data available.
We started out with Lean. That's a formal language for proofs. So we had a question, prove that. We turned that into Lean code. Then after the Lean code, there's a theorem and then begin and end. And then learn the Lean tactics for proving. And then once we had the proof, I'll show a screen. At the end, I have many slides that I didn't show. So essentially, we started with Lean, but we found out that the questions that we were able to prove with Lean were quite simple and quite brittle. And our goal is now to make something more robust with proofs, with more advanced questions.
But did you have to like fine tune on a bunch of lean code to get this to work? Was that
We-
something that was
We
part of
had to, so let me show you. We had to create a data set. Let's share screen again. Create a data set of lean and tactic code pairs. So it was trained on a data set of these things. Yeah.
I see. So, okay, so you have some large scale data set of these.
Yeah.
Proofs, and I see. Is
So
that
now
available, or is
we're
that
working
still-
on benchmarking this, saying, okay, with images and proofs. So images to captions, we do X%. But images to program representation, synthesizing LaTeX code using TXZ package and drawing package, we have X plus Y percentage. I can just give a teaser, but this is in progress and will be submitted soon. So, but just a teaser, you have the original LaTeX and the image import. So you include graphics, right? And you generate this image. But this same image can also be generated using other methods. It can be generated using LaTeX code, using a package, okay? And the same goes for this. This image can be imported, but you can generate a code LaTeX representation that actually synthesizes this image. So we're thinking that the same idea of a program synthesis, of a program representation that was so beneficial for the math and STEM problems, a similar, different LaTeX drawing representation for images is an intermediate representation that we hope will improve upon the percentage of accuracy that we get just from downloading archives, PDFs and text and captions. So we hope to show these ablation studies soon and say, how much does using a program synthesis representation help when you're interpreting images over straight up text and image, right? Text to image. There are many models of text to image recently. And there's a large data set, an archive of PDFs and LaTeX. So the question is, the interesting question we're looking into is to quantify the delta of program synthesis. How much does that help there for images and also improves? Because we realized that this program synthesis and program representations really helped in STEM and math.
Right. Is any of the work on proofs available, or is that still?
It's in progress, and we'll make it available on publications.
Okay. All right. Are there any other questions?
Oh yeah, I have one quick question. So you said you did clustering on all of the incoming questions. Did you do any clustering or like dependencies with the synthesized programs to see like, I don't know, like knowledge of this requires understanding of these two combined topics or something like that? Or?
Yeah, let me share screen. So what we did is, here's an example of an early visualization we did, a different one. What we did is we asked two things. We asked which courses help few shot other courses. So instead of few shotting within the course, we said if we few shot, say, machine learning with calculus and linear algebra, does that help zero shot machine learning? And if so, that means that we can generate a graph of relationships between questions or between courses and say calculus and linear algebra should be prerequisite to machine learning, but not because this has been deemed by history or other people, but because we see this in the data. Okay, we embed the questions that way. Does that answer your question?
Yeah, thanks.
Okay. Are there any other questions? Okay, yeah, thanks so much for the great talk, Iddo, and thanks everyone for joining. And I guess I'll see you next time.
Okay.
Thanks. Bye, everyone.
Bye.